The first thing I want to do a deep dive on today is on failure modes for estimators of heterogeneous treatment effects. The motivation for this is that often in an engineering setting, someone will propose and advocate for a machine that does something. They'll tell you that it works, but then you can look at some performance diagnostics and is the machine working or not? It's kind of hard to tell. Generally, what's considered a best practice is that if a machine does a job well, it solves some problem you might have had. So first, you demonstrate the problem. You try to argue the problem is difficult to solve. Then you show that the machine solves the problem. And at least that gets some confidence that the machine is doing something useful. So this is kind of the approach I'm going to take with methods for treatment heterogeneity in observational studies. I'm first going to show you some things that can go wrong. Two things in particular I'm going to worry about are regularization bias and confounding bias. And then I'm going to discuss how you can design methods that avoid these problems. And so throughout this part of the lecture, I'm going to go by kind of example. I'm going to show kind of a series of baselines, methods for a treatment heterogeneity, talk about when they work, when they don't work, and kind of by seeing these methods, how they work or not work, you can kind of get an understanding of what regularization and confounding bias are in practice. But so in terms of baseline methods, the simplest thing you can do is based on the following direct observation. Remember, we're working under unconfoundedness. The treatment is as good as random, conditional on X. Then kind of following the same kinds of calculations we saw in lecture 2, you can see that the conditional average treatment effect, that is the following thing, can be written as a difference, mu1 of X minus mu0 of X, where mu1 of X is the expectation of Y given X and treatment equals set to 1, and mu0 of X is the expectation of Y given X for controls. So the point here is that these two problems here, mu1 of X, mu0 of X, these are just non-parametric regression problems. So we could kind of attempt to learn how to predict Y from X and W directly, and then try to learn mu1 of X and mu0 of X, take their difference, call that an estimate of tau hat of X, and this would kind of obviously be consistent given enough data. So to be a little more specific, you could try doing this in two ways. The first is, and here I'm going to follow nomenclature from this recent paper by Kunzel et al. There's a reference to it in the course outline. So a first thing you could do is what's called the T-learner, is you could try to solve two different regression problems. First, you're going to estimate mu hat 0 by predicting Y from X on the controls. And then you're going to learn mu1 of X by predicting Y from X on the treated. And then you take the difference of these two regression estimates. It's called the T-learner because you run two regressions. But beyond that, it's just a very different direct application of kind of the identity here. Essentially, tau of X is mu1 of X minus mu0 of X. That relationship is true. Then the T-learner just puts hats on everything. It estimates mu hat 1 of X and mu hat 0 of X by a kind of any type of non-parametric regression, and then sets tau hat to be their difference. So that's one thing you could do. Another very similar thing you could do, but kind of algorithmically looks different, is that instead of predicting Y from X on treated and control separately, you could just kind of glob your X's and W's into a single covariate, call it Z, and learn to predict Y from X and W simultaneously. So now you have just a single mu hat function that you can give it covariates and a treatment status, and then predict from, and then make a prediction there. And then you could kind of query the same mu hat function twice ones with treatment set to 1 and ones with treatment set to 0, and get predictions tau hat of x out of that. This is called Exlearner because you're in a single regression. Okay, simple enough. So far, I've been kind of very open-ended about how you'd actually implement this. You need to choose some method, right, to predict y from either x and x and w. There are different choices you could make. Here, I'm going to show some examples using random forests, kind of just because they're easy to run. You could really kind of do this with any other approach. So, okay, in order to kind of understand a little bit of what's going on here, I'm going to show just kind of a couple slides to remind you about how trees and forests work. I know you've already seen it so far, but it's just to kind of, in diagnosing what could be going right or wrong, it's just kind of helpful to remember what's going on, specifically in the algorithm. If you ran this with lasso or boosting in the simulations, you might see similar results as to what I'm going to show later on, but kind of understanding step by step how that happened might look a little different. So anyways, what's a random forest? A random forest is a method that kind of try to predict y from x. So it's just kind of this black box predictive method, and exactly of the type we wanted before. How does it operate? Well, essentially each tree on its own, it's going to kind of subdivide a space into rectangles, and it's going to average, it's going to predict at this point x by averaging outcomes for everyone who falls within this rectangle. A random forest is going to aggregate trees. So just very quickly, we've already seen this before, trees kind of are going to zoom in on which rectangle you split in by kind of recursively partitioning the feature space. This is a somewhat unstable procedure. So then kind of back in the day, there was a lot of discussion of kind of if you're training decision trees, if there are many different ways you could have trained a decision tree that all look similar or perform similarly, which one should you choose? There was this something people worked hard on until kind of at some point people realized you're better off not choosing. Just kind of, if there are many reasonable looking trees, just train all the trees and kind of get a consensus prediction as their average. And that's what kind of an forest paper by Bryman does. And so really kind of pictorially, if you have a bunch of trees here, one tree predicts by averaging the outcomes in this leaf, and another tree predicts by averaging the outcomes in this leaf, and so forth. And the random forest is going to predict by just averaging the predictions by made by all the trees, so it's kind of a double average. So this is what's going on. There are different ways to kind of increase the diversity of the forest, but kind of this is enough to understand what is going on with the T-learner and the S-learner. So anyways, what is the T-learner doing specifically? For estimating mu hat 0 of x, it's going to train trees that kind of try to find regions where kind of your best prediction of y given x is roughly constant. It's going to make separate predictions in each of these regions. Then if you do a forest, you're going to do this with a bunch of trees and average those predictions. You're going to train different trees to predict y from x on the controls versus on the treated, and then tau hat is going to be this difference. The S-learner is going to do something different. It's going to try to build trees where kind of at each point you choose, do you make a split on one of the x's? That is kind of, do you create heterogeneity? Or do you make a split on w, which is kind of means creating a treatment effect? So from a treatment effect estimation point of view, the S-learner random forest algorithmically might look a little strange, but kind of in terms of black box prediction, okay, this is just what it looks like. So this is what's going on here. How good are these methods for treatment heterogeneity? Let's try it out. And just before going there, I just kind of wanted to, in case you want to copy paste on the slides, here's kind of a few lines of code that implement the T-learner and the S-learner using the regression forest function for random forests. All right, how well do these do? And here's kind of a very simple simulation exercise for estimating treatment effects. So you see, I'm running a simulation with 4,000 samples in 10 dimensions. The probability of being treated is 0.3. And the salient point here is that first treatment is everyone is treated with probability 30%. So this is a randomized trial. There's no association between any kind of unit characteristics and their probability of being treated. So this is kind of, from a causal inference point of view, makes the problem a lot easier. The second is you have this conditional average treatment effect function. I'm calling it tau here. It's also very simple. It's actually just a logistic shape in X3. If you knew that kind of the conditional average treatment effect had a logistic shape, you could recover it kind of very easily by a parametric modeling. But okay, the point is that with machine learning, you don't need to know the parametric model a priori. We can kind of discover it from data. And then there's going to be this baseline effect, max of x1, x2, and 0. This is a little more complicated. So essentially, this is setting that's supposed to be super easy if you're doing the right thing. The study is randomized, so there's no confounding. The treatment effect function is very simple, so you're kind of focusing on the right objective. You should just nail it. But there's this kind of more complicated interactive baseline effect that, if you're not careful, might cause you problems. And how does everyone do? Actually, like pretty terrible, right? So here, kind of, I'm plotting. Remember, the conditional average treatment effect was just a function of x3. So I'm plotting kind of on a test set for each data point. The true kind of here in true red, you see kind of true relationship between x3 and the conditional average treatment effect here. And in black, you see the estimates from the T forest or the S forest. And you see it's kind of disastrously bad. The T forest is just kind of very, very spread out. And the S forest not only is it spread out, but it's kind of systematically biased and underestimating the size of the treatment effects. So this is somewhat concerning. You might have hoped for better, right? Because I just kind of started by writing tau of x as mu1 of x minus mu0 of x. Let's estimate mu1 of x. Let's do so using a forest. Forests are okay. Let's estimate mu0 of x using a forest. Again, forests are okay. And you think you're doing something okay, and then you kind of get this very bad empirical performance. So what went wrong? And the problem is essentially, I think I was calling earlier, regularization bias. So to understand this, I like this picture from this paper by Kinson et al. I mentioned earlier. What they're imagining is estimating treatment effects in the following very, very simple study. Here, x is one-dimensional, so you only have one covariate. Y is also one-dimensional. It's a randomized trial. And I'm plotting all the data. So each control point is x, and each treated point is a blue dot, red x for the control points. And the only wrinkle here is that you have a lot more control points than treated points. Okay. What's the treatment effect here? By eye, it's kind of clear, right? There's this difference between the treated and controls is kind of always 1. So kind of by eye, you know that the treatment effect has to be 1 here. But what happens when we try to estimate the heterogeneous treatment effect? Let's try doing so using the T-learner approach. So what I'm going to start by doing is, remember the T-learner approach, what it does is it first estimates mu hat 0 of x. It predicts y from x on the controls. Then it estimates mu hat 1 of x. It predicts y from x on the treated. And then it takes the difference. And so what's going to happen here? Well, let's say I run a tree. So I'm going to kind of I'm going to first run a tree on the controls, and I'm going to see that the signal changes here and that the signal changes here. So I'm going to do a very good job kind of. Here's one leaf and my treatment effect here. Here's another leaf and my treatment effect here. And here's a third leaf on my treatment effect here. And you could say this tree is very good. The task was to fit y from x among the controls. There was kind of an obvious region in the middle where there was a shift in the response function, and you found it and you adapted to it. So kind of a well done tree. Very good. So now the next thing we need to do is estimate mu hat 1 of x and predict y from x on the controls. We're again going to use a tree, but here we have less data. Do we see any jumps in the data, obviously? I mean, when you know there should be a jump here and here, you kind of see it. But honestly, a kind of well-tuned tree, given just this data, it probably doesn't see any patterns at all. So your tree does the reasonable thing. If you don't see any evidence that you should split, just don't split. So we estimate the expectation of y given x as essentially a constant function. And again, that's very good. So we're in good shape. We did a great job fitting mu hat 1 of x. We did a great job fitting mu hat 0 of x. And then what are we going to do at the end? Remember, what we want is we want to fit tau hat x is equal to mu hat 1 of x minus mu hat 0 of x. And we've done a great job fitting both mu hat 1 of x and mu hat 0 of x in this picture. But now we take their difference, and what do we get? Their difference, tau hat of x, well, here, it's big, it's big, it's big, it's big, it's big. You have a big treatment effect. Now you have this middle zone where suddenly you have a very small treatment effect because mu hat 0 kind of got bigger. And now again, you get a big treatment effect at the end there. And wow, there's a lot of treatment heterogeneity, right? These people here and these people here really benefit from the treatment, but these people in between here, not so much, right? All right, so it looks like we found treatment heterogeneity. But this is obviously very bad, right? We agreed that there's no treatment heterogeneity in this picture. The treatment effect is constant at 1 the whole time. And kind of the worst thing you can do in data analysis in general is to claim that you found something. You found heterogeneity, you found a signal in a case where there's none. So that kind of in such a simple problem, you could be tricked into thinking there's heterogeneity when there's none is really unexcusable. What went wrong? Well, the problem is that essentially you were using machine learning, and of course machine learning regularizes, has to kind of adapt to the shape of the function, and you didn't adapt to the shape of the function in a way that kind of recognized the task at hand. When you were fitting the function of the controls, when you were fitting this red line, you had a lot of data. So you were able to kind of very kind of accurately see any changes in the data and respond to them. So you kind of regularize very little, fit the function aggressively, that's good. In fitting this blue curve for the treated units, you had less data. So what do? You don't introduce as many splits because you don't have enough data to kind of put more splits. Effectively, you're regularizing more. You're pushing your function more towards a simpler thing. And that's, again, good. But then what happens is you have a discrepancy between how much you regularized the function on the treated and the controls. You regularize your function on the treated a lot and very little on the controls. And then just because you regularize kind of this part of the difference very little and this part of the difference a lot, then you kind of inconsistently regularize tau hat, and this kind of heterogeneity emerges somehow, apparently, in the difference, and that's no good. Okay, that's regularization bias. What I'm emphasizing here is just kind of tau of x. It's true that tau of x is mu1 of x minus mu0 of x, but that doesn't mean that kind of machine learning based approaches that kind of directly are motivated kind of by this functional equivalence without being careful about what they're doing estimation wise would be any good. So that's regularization bias. What can we do about it? And notice that regularization bias is something that kind of arises even in randomized trials. Last week, Susan talked about causal trees as kind of one algorithmic way of avoiding this problem in the case of trees specifically. Here, just to kind of, still want to talk about these topics, but to kind of show you some other ideas also on how to avoid this problem. I'll talk about the Exlearner, which was introduced by this paper from which I'm taking the pictures. So what they wanted to do is they're like the T-learner, the S-learner, they're very nice in that you can just write them down as kind of a generic recipe. You have a generic recipe for predicting Y from X. You can just apply it and turn it into a treatment effect estimator. They like that aspect of it, but just kind of didn't like that it gives you a lot of regularization bias. So the Exlearner is an idea that kind of does the same thing, but in a slightly fancier way. We're going to start by fitting mu hat 0 like before, predict Y from X. Then once we fit Y from X, we on the treated units kind of predict mu hat 0 of X. So this kind of crudely you could be thinking as trying to impute for each treated unit what would have happened if you gave them control. And then look at delta I1 of X. That is kind of the difference between the actual outcome for the treated unit minus kind of your best guess of what you might have seen, what you might have had had you received the control outcome. And this is kind of, you could think of this as a noisy proxy for the individual treatment effect, yi1 minus yi0. If this functional form looks familiar to you and reminds you of synthetic controls, that's a good thing to be thinking about. It's a very different application setting with very different considerations, but the kind of estimator structure looks very similar to what's done in synthetic controls. So they do this once, and so they do this, and then the way they're going to estimate the conditional average treatment effect function is essentially by, on the treated units, regressing these differences, yi minus mu hat 0 of xi, that is actual treated minus imputed control outcome. They're going to kind of regress these delta i's against x non-parametrically. That's, again, a prediction problem. You predict delta I1 from xi on the treated units, and that gives you a first estimate tau hat 0 of x of the treatment effect. Then what they do, that gives you first estimate tau hat 1 of x of the treated units. And then what they're going to do is they're going to swap roles. So they're going to estimate mu hat 1 from the treated. On the controls, look at actual outcomes, actual control outcomes. Look at mu hat 1 of x minus yi on the controls as another kind of proxy for the HTE, and then estimate tau hat 0 from there. And then they're going to pool these and turn tau hat, estimate the final treatment effect as a weighted average of these two Kate functions you estimate on the treated and the controls. The thing to note here is this last step, the use of the propensity score E hat is just heuristic. But the thing to note is kind of if most people are in the control, then E hat of x is going to be pretty close to 0. So then kind of you're essentially just going to use the tau hat of x function that you get by first learning to predict y from x on the controls and then taking these difference on the treated. So again, if you want, code using forests. But how does this work? Kind of much better. This function, you might be disappointed that, okay, shouldn't good predictions have kind of the black dots lie on top of the red dots, like you would kind of if you had perfectly fit a parametric model? You might hope for that, but you never get that of machine learning. Kind of one theme really emphasized in the lecture on average treatment effects is that machine learning methods, you should hope that they're almost always pretty good, but never perfect. And this kind of X forest kind of in predicting the condition average treatment effect from X3, I think lives up to that goal. The black dots have the same shape as the red dot, but they're not perfect. And certainly this is much, much better than the S and the T forests. So why was this better? I think it's helpful to kind of consider the same pictures before. So remember the Exlearner starts by kind of fitting the same kind of red and blue curves we had before. But then what it's going to do is it's going to take, it's going to estimate these delta I terms. So kind of these imputed treatment effects. So the way you can think of this is on the picture is kind of for every blue dot, you're going to draw a curve down to the red curve. And you're going to think of these as your delta I1s. These are your kind of imputed noisy proxies for the individual treatment effect for treated people. Similarly for controls, you're always going to look at the blue curve as an imputed what would have happened to me under treatment. So we're going to draw all these lines here. Okay, there's way more of them. And we're going to look at these. These are going to serve a symmetric role. They're going to be kind of what we would have called delta I zeros on the previous slide. And then, right, the Exlearner is going to estimate the Kate by predicting delta I1 from X and delta I0 from X. And how does this work? Well, it turns out that kind of here, remember, the red curve here was very good. We got the shape, mu hat 0 of X is very accurate. So then these blue lines are going to be kind of good proxies of the treatment effect. So if we're going to try to estimate tau of X by regressing these blue lines on X, we're in good shape. On the other hand, the blue curve, the estimate mu hat 1 of X, wasn't so good. So these red lines are going to be much less good proxies for the treatment effect. Like they're pretty short here, but they're much longer here. So when we actually get this, then we're going to get tau hat 1 of X. That's the thing that kind of predicted the delta I's on the treated. It's going to be a very good estimate of the treatment effect, essentially constant. We're going to also get this tau hat 0 of X, which is going to be quite bad. But then kind of remember that Exlearner kind of tries to pool tau hat 1 of X and tau hat 0 of X in a way that if most units receive control, then it's really just going to upweight tau hat 1 of X a lot. So then the kind of final prediction of the Exlearner is going to be some weighted average of tau hat 1 and tau hat 0, but it's essentially just going to give you this blue curve here, which again is what we wanted, an accurate estimate of essentially a constant treatment effect at 1. So this is what's going on. Kind of the Exlearner looks a lot like the T-learner and the S-learner, and there's kind of a recipe where you just solve a bunch of prediction problems in a row. But kind of by being more careful about the recipe design, you got better results and are more robust to regularization bias. So this thing, you can use it. It's cool that in my experience, the Exlearner in randomized trials works very well. And it's kind of very easy to implement because it only requires prediction. So that's kind of a good thing to know. All right, so that was regularization bias. The next thing I wanted to worry about or thought we should worry about is confounding bias. That's what happens when you're outside of a randomized trial. Your treatment assignment probabilities vary with X, and this relationship may be problematic. And again, to get started with a simulation, here we have a similar setting, except now the treatment isn't assigned uniformly at random. Now kind of there's a logistic shape in terms of X3, where kind of the bigger X3 is, the more likely you're going to be treated. On the other hand, the treatment effect is constant here. So if you kind of get rid of all the confounding, the treatment heterogeneity problem is trivial. There's no heterogeneity. There's a constant treatment effect of tau equals 1. But now there's more confounding because you'll notice not only does your probability of being treated kind of vary with X, but actually generally the bigger X3 is, the bigger Y is going to be on average. So there's this kind of correlation between your baseline effect and treatment assignment probability. So if you don't address the confounding, well, you're going to end up in trouble. So what happens? Well, the T forest is outright terrible. The S forest is also outright terrible. The X forest here isn't quite as bad, but it's definitely not good, right? Like the X forest, it thinks that there are bigger treatment effects here than here, for example. It seems to be finding some heterogeneity where there is none. And kind of the overall, all three methods here, even though we saw that the treatment effect is constant at 1, there's no heterogeneity. All of these methods hallucinate heterogeneous treatment effects. I should emphasize the word heterogeneous on the slide also. They all kind of hallucinate heterogeneous treatment effects here, even though the treatment effect is constant. And why is this? Well, again, the theme conceptually is very closely related to what we saw earlier. The propensity score here isn't constant. If the propensity score isn't constant, you should be worrying about how are you adjusting for that. When estimating the average treatment effect, using AIPW was a nice way of doing this. We need to also be able to adjust for propensity scores if propensity scores aren't constant in this setting. So that's going to be the focus of the next part of this lecture. But so just to recap this first part, right? There are many things to worry about when fitting a treatment heterogeneity. There's regularization bias. There's confounding bias. Regularization bias is always there, but even in randomized trials. But there are many ways to address it. The kind of causal tree construction you saw last time is a kind of very direct way of doing that. The Exlearner is also a nice way of addressing regularization bias using kind of this prediction recipe type approach. But okay, in observational studies, there's also this other type of bias, confounding bias. And dealing with that is a little trickier. We're going to need to bring the propensity score to the table again. And we're going to need to be very careful in kind of separating the treatment effect component of the problem from the confounding component of the problem, and find ways to kind of eliminate the confounding component while kind of appropriately fitting and expressing the treatment effect.